So before watching this video, which is aiming to solve this problem for spectroscopy, make sure you know your basics about the chemical shifts for C13 and proton NMRs, and make sure you know about how to get the multiplicities and what they mean. Okay, I will try to explain it briefly, but you definitely need to make sure you know the NMRs concepts and then look at it. All right. Okay, so that being said, let's start with what we have in hand. So the first thing that you need to do in an NMR is to see if there are proton counts given in the spectrum. So sometimes the protons can be the same number of protons that you have in the molecule that you see in the spectrum. Sometimes they could be multiples or fractions of what actually you have in the molecule. Okay, so for example, if you look at this, you have 11 carbons, 20 hydrogens, right? And here you have 6 plus 2 plus 1 plus 1. You have only 10 hydrogens here. What that tells you is this molecule is symmetric, and you are going to have to find the one half structure, which is obviously going to help you understand what the other half is. Okay, so that's that. And also C13 NMR is also going to be useful. So what the C13 tells you here is you have 4 aliphatic carbons, which means carbons that are sp3 hybridized, okay, and 2 carbons that are sp2 hybridized. Now both these carbons could be alkene carbons, or this could be an alkene carbon and this could be an aromatic carbon, right? This is definitely an alkene carbon because it is close to 100, 110, whereas this one is above 150. So then based on the ppm values, you might say that this could either be an aromatic compound or an alkene carbon. All right, now how do we know whether it's an aromatic or an alkene carbon? Okay, so the first thing is, usually if you have a benzene ring, unless you have all 6 of the benzene carbons substituted with the same group, you're not going to have a single benzene carbon. All right, therefore this is not going to be a benzene carbon. This is actually an alkene carbon, which is probably when you see carbon carbon double bond, you might actually be looking at both carbons that are separated by this much ppm value. Okay, that's one. And also, if you look at the maximum number of hydrogens this molecule can have, if you had a open chain hydrocarbon like an alkane, right, you will expect that for 11 carbons to have 24 hydrogens based on the 2n plus 2 rule, and you have a difference of 4. What that tells you is that you have 2 double bond equivalents in the molecule. What is a double bond equivalent? It is either you have 2 double bonds, or 1 triple bond, or 1 cyclic structure and 1 double bond, or 2 cyclic structures in the molecule. So that's what this tells you. Okay, so we'll find out which one is what. Okay, so that's what. So if you have a benzene ring, by the way, right, if you have a benzene ring, then you are going to have a total of 4 double bond equivalents at least in the molecule. You need to have at least 4 double bond equivalents based on your molecular formula to be able to say whether you have a benzene, to be able to say that you have a benzene ring, right? So since you have only 2 double bond equivalents, this cannot be a benzene ring or an aromatic ring containing structure. Okay, all right, that's that. So we just established that we have 4 distinct alkyl carbons and 2 olefinic carbons in the molecule. Okay, all right, so let's go with that. And now let's see what we have here. You have 6 hydrogens corresponding to a singlet in the spectrum, and as I just mentioned, that means you have 12 hydrogens corresponding to a singlet. Based on where this group is, right, you can say that these are going to be most likely CH3 hydrogens. And since each CH3 has 3, if we have 4 of these CH3 hydrogens, then you have a total of 12 hydrogens that are represented by this singlet here. And the fact that it is a singlet and it is not split by anything else tells you that the carbon that is attached to this methyl group are attached to other carbons. Okay, this carbon does not have a hydrogen. If it had a hydrogen, one hydrogen, this will be a doublet, right? It is not a doublet, it's a singlet. That means that this carbon that is attached to this carbon is actually a tertiary carbon. It is attached to 3 other carbons. Okay, that's one piece of information. you should know. Now the second piece of information that you can get from the multiplicities is that you have a triplet that can correspond to 4 carbons. Okay, so if you have a carbon, right, and this carbon is attached to a hydrogen and this signal is coming out of that hydrogen, okay, based on the proton count, it says that we have 4 hydrogens, but you cannot have 4 hydrogens, right, and 1 carbon next to it with other groups attached to it, because if you already have 4 hydrogens, then you have already saturated the carbon. What that tells you is there are 2 CH2 groups, right, 2 CH2 groups which has a total of 4 hydrogen count in the molecule that has 2 hydrogens next to it. So I'll tell you what I mean by that. Okay, so we just established that this carbon cannot have 4 hydrogens. It can have only 2 hydrogens, which means you have 2 of these CH2s, which gives you this triplet. And what that tells you is that there is a CH2 next to this. Okay, there is a CH2 next to this, and since the 4 hydrogens are coming out of the CH2, that means you have 2 CH2s which are exactly the same. Okay, so let's say this is Ca, and this also has to be Ca, and this is Cb, and these 2 hydrogens are splitting the CH2s in the Ca into a triplet, and since these 2 are the same, they will appear as a single signal, and these 2 hydrogens will split these 2 CH2s as a 2 plus 1, which is a triplet that you are seeing here. All right, and that pans out to be true when you look at this quintet. If you look at this quintet, which is 5 splitting of 5 small peaks, it tells you that these 4 hydrogens are splitting this into a quintet. So when this Cb hydrogen is appearing here, right, these 4 hydrogens, which are the same hydrogens, are splitting this CH2 into a quintet. Okay, so that's that. So we just established this part, we just established this part, we also established this CH3s in the molecule. Okay, now we should somehow be able to piece all these things together. We'll just look at that. Now let's also recognize the fact that you have a singlet at 4.8, 4.9. What that tells you is you have a double bond in the molecule. All right, now if you multiply this by 2, that means you have 2 hydrogens, and those 2 hydrogens can either be like this or they can be like that. Okay, with the rest of the molecule being the same. All right, so based on all these information, right, you can write multiple structures, and one of the structures that will match that is probably going to have a CH2 CH2 CH2, where okay, these 2 CH2s are the A CH2s, so A here, and that CH2 is a B CH2. All right, okay, now what we can do is we can now look at how to get the CH3 here. All right, the CH3 here. Now the only way to get 4 CH3s is if we have something like that. Okay, something like that. So because we are trying to keep this molecule symmetric, remember, all right, therefore if you put CH2s on one side, right, then you had to put CH2s on the other side as well, and now we have to try to accommodate a double bond, right? So maybe one way to do that is put an alkene like that. Okay, put an alkene like that. So if you look at this 1 2 3 4 5 6 7, okay, and then you have 4 methyl groups in this molecule, and this is one of the structures that is possible for this carbon 13 and also for this proton NMR. Now there's only one hitch in this structure for the carbon 13, right? This perfectly explains the proton NMR you're looking at here, right? Because these methyl groups are going to be singlet, these 2 hydrogens are the same, therefore it is going to appear here. Everything else matches. The only thing that doesn't match is you having 2 different, okay, alkene carbons. Based on this structure, which is a 7-member ring, these 2 carbons are exactly the same, therefore you won't be seeing 2 distinct carbons. All right, so this explains almost everything except this one problem where these 2 alkene carbons are different. Okay, so here, as I just mentioned, these 2 alkene carbons are the same. So one way to write is now have something like this. Okay, have something like this. So now you have 4 methyl groups and a carbon double bond with 2 hydrogens here. So this is 6 carbons, 7, 8, 9, 10, 11. All right, so that's what matters here. This is also obviously 7 plus 4 is 11. All right, so this is fine except for that problem. But whereas here the alkene carbons are different. This carbon is different from this carbon, and I would think that the carbon that is attached to 2 other carbons is the 160 carbon, and this carbon that is the primary carbon is the one that you have here, and the other 4 alkyl groups are 1, 2, 3, and 4. Okay, carbon, 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 and carbon. So that explains what we basically have in hand. Okay, so hopefully this makes sense, and this is the way you typically approach a carbon and proton NMR problem.